Today I want to give you a crash course on the Schrödinger equation. This is the central equation in quantum mechanics that helps us calculate lots of quantum phenomena. So here it is, H psi equals E psi. Put a box around that, that's the Schrödinger equation. H is the Hamiltonian, and it's an operator. I'll tell you what that means in just a minute, but it's going to give us the energy, all right? Psi is the wave function of the particle, and the wave function has a few interesting properties. So one is that the shape of the wave function tells you everything about what the particle is doing, and it tells you the energy, it tells you the momentum, it tells you the angular momentum if it has any, and it also tells you essentially where the particle is or where you're most likely to find it when you go to look for it. So for example, the absolute value squared of the wave function is the probability of finding the particle in any given region of space. Now, because it's a probability, if you're talking about a single particle wave function, that means when you integrate that probability over all space, you better get a 100% chance of finding the particle somewhere. So we write that down mathematically as integral magnitude of psi squared over all space equals 1. Psi itself is a complex valued function, meaning it can involve imaginary numbers as well as real numbers. Now on the right-hand side of this equation, we have E psi. E is a real number and it's the energy. So it's going to be something like 5 joules or 13 electron volts. Now, that's it. That's the Schrödinger equation, but let's unpack the pieces and see what they're all about. The Hamiltonian, because it's related to the energy, needs to have some kinetic energy piece as well as some potential energy piece. So we'll write Ke plus Pe for kinetic energy plus potential energy. Kinetic energy is the familiar 1/2 mv squared. Now in quantum mechanics, we like to rewrite that in terms of the momentum as p squared over 2m, where p is momentum and m is the mass of the particle. For the potential energy, we'll just write V of r. The of r means that it's a function of position r. And so, for example, if we put this in the context of the hydrogen atom, let's say you're trying to calculate the wave function of an electron in the hydrogen atom. The nucleus of that is a proton, and the proton is so much heavier than the electron that we pretend the proton is stuck at one spot in space and that the electron swarms around that, and we're going to calculate the wave function of that electron relative to the proton's position. Now, where's the potential energy? It's because the electron is negatively charged and the proton is positively charged. So these guys attract each other, and their attraction is the Coulomb attraction. So it depends on the charge of the proton, plus E, the charge of the electron, minus E, and it depends on the distance between them. And so we write that as the potential is proportional to E squared over R. So this means, as they get close together, their energy becomes a large number that's negative. So that's what that minus sign in front of it is to help us remember, is that they're attracted to each other. They want to be close together. Now, here's probably the strangest thing about how we write down momentum in quantum mechanics. Are you ready? We write it down as P, momentum, equals minus I h bar d by dx. H bar is Planck's constant. I is the imaginary number I. It's the square root of -1, and d by dx is the first derivative with respect to position. So why do we write it that way? It is very strange. We could give you a long mathematical proof about why that's the right way to do it, but ultimately it boils down to this. We write it down that way because it works. Okay, so take it as that for right now. We write it down that way because it works. So now let me put that into what we have so far for the Schrödinger equation in the context of, say, the hydrogen atom. The Hamiltonian is kinetic energy plus potential energy. Our kinetic energy we'll write now as P squared over 2m equals minus h bar squared over 2m d squared by dx squared plus the potential energy. Let me just write that as V of R. We'll keep it general. It could apply to something other than the hydrogen atom, for example. Maybe you have a particle in a well, that sort of thing. So to solve the Schrödinger equation, here's what that means. You take the left-hand side of this equation. Now on the left-hand side, that Hamiltonian, you'll see, isn't just a number, it's what we call an operator because it involves derivatives because of the strange way that the momentum gets expressed in quantum mechanics. So here's what you do. You calculate the left-hand side, which means you'll let that second derivative operate on the wave function psi. Look at what you get back, and if you happen to get the exact same wave function times a number, a single number, then you say you have solved the Schrödinger equation. And the number that it gives you back in front is the energy. And so that's the way in which the Hamiltonian is related to the energy. The solutions come in an infinite set. Okay, so for the hydrogen atom, for example, there's an infinite set of solutions, and they're organized in the following way. We'll say that there's some ground state whose energy is E naught, and that corresponds to a particular wave function, psi naught, and that's the ground state, it's the lowest energy state, and we would say that E naught is the eigenvalue and psi is the eigenfunction. And then there's a first excited state, which we label E1, and it corresponds to psi1, and we would say that in that case, the eigenvalue is E1, and the eigenfunction is psi1, and then so on and so forth. And there's an infinite set of those. That's what happens with the hydrogen atom, or for example, with a particle in a box. And that's your crash course to the Schrödinger equation.